Welcome back to All About Rx. Today we're simplifying one of the absolute most important topics in organic chemistry, aromaticity. We're going to take these detailed notes and turn them into a totally clear, dynamic explainer so you can absolutely master this concept.
Okay, let's just dive right into it and clear up a massive misconception right off the bat. Forget the idea that aromaticity is about how a molecule smells. I know, the term was coined in the 1800s because a lot of these early compounds just happened to be fragrant. But today we're talking about strict structural and electronic rules, not what your nose is picking up.
So, what actually is it? Well, you can think of aromaticity as basically the highly exclusive, super stable VIP club of the molecular world. It's a collection of special properties that make a ring remarkably stable compared to standard molecules. We're talking massive stabilization energy, highly delocalized pi electrons that just freely circulate, and a strong preference for substitution reactions rather than addition reactions, mostly because an addition reaction would ruin that perfect structural harmony.
Now, how do we actually know if a molecule gets into this VIP club? It's simple. We use a theory proposed by Huckel back in 1931, and we can boil it down to a foolproof cheat code, the CP-CH test. A molecule absolutely must pass all four of these strict conditions. Let's break them down. The first three conditions are all about the physical architecture. Condition 1, the first C, cyclic. The molecule must form a closed loop, or ring. Condition 2, P, planar. Every single atom in that ring has to lie perfectly flat. Why? Well, that brings us to the second C, fully conjugated. By lying completely flat, every single atom's p orbital can align perfectly, allowing for this beautiful continuous electron delocalization all the way around the ring.
And that brings us to the final condition, the H, Huckel's rule. This one is a strict mathematical test. The ring must contain exactly 4n plus 2 pi electrons. In this formula, n is just a whole number, like 1, 2, or 3. So if you plug those in, it gives us totals of 2, 6, 10, or 14 pi electrons needed to achieve that magical stability.
Look at benzene here. It is literally the perfect aromatic model. It ticks every single box. It's cyclic, it's planar, it's fully conjugated, and if you look at its 3 double bonds, that gives us exactly 6 pi electrons. That fits Huckel's rule perfectly when n equals 1. And that right there is exactly why benzene is famously so incredibly stable.
But you might be wondering, what happens if a molecule looks super similar to benzene, but it fails the test? What if it misses these strict mathematical and structural criteria? Well, it's not just a simple pass or fail. There are actually 2 different ways to fail, and they have vastly different consequences.
First, we have anti-aromatic molecules. These are cyclic, they're planar, and they're fully conjugated, but they have an even number of pi electron pairs, meaning they have 4n electrons instead of 4n plus 2. This makes them highly unstable and dangerously reactive, like cyclobutadiene. On the flip side, we have non-aromatic molecules. These simply fail any one of the 4 criteria. Maybe they aren't fully conjugated, or maybe they just aren't completely planar. They don't have the crazy stability of aromatics, but they avoid the chaotic instability of anti-aromatics.
Now keep in mind, a molecule doesn't actually need a classic 6-carbon benzene ring to be aromatic. We have benzenoids, like toluene, which do contain that classic ring, but then we have non-benzenoids, like azulene. Azulene is completely aromatic, but it relies on an integrated system of 5- and 7-membered conjugated rings to achieve that necessary continuous electron flow. Pretty cool, right?
Okay, so why spend time on this? Why does this specific molecular cheat code actually matter outside of passing your organic chemistry exams?
Because aromaticity is literally everywhere. Industrially, it is massive. We're talking about 35 million tons of aromatic compounds manufactured globally every single year. They're the foundational building blocks for industrial plastics you use every day, like nylon, polyester, and polystyrene.
And biologically, it's even more mind-blowing. These aromatic scaffolds are at the very core of your biology. They make up the bases of your DNA and RNA. 4 of your essential amino acids are aromatic. Critical vitamins, like B and K, rely on them. They form the core of heme in your blood and chlorophyll in plants. Even super common life-saving drugs like aspirin and ibuprofen completely rely on these stable aromatic scaffolds to actually work inside your body.
So remember, CPCH, cyclic, planar,
Conjugated, and Huckel's rule. Go ahead and screenshot this quick recall summary slide right now so you have the ultimate high-yield breakdown saved for your studies. If you found this high-yield breakdown helpful, make sure to like and subscribe to AllAboutRx for more chemistry lectures. Links are in the bio.
But before you go, as you dive back into your chemistry studies today, consider this. If Huckel's strict mathematical rule didn't provide such incredible resilient stability to these molecular rings, would the DNA in our very cells even be able to hold itself together? It is just amazing to think that the building blocks of life itself depend on the perfect alignment of p orbitals. Thanks for exploring this explainer with me, and I'll catch you in the next one.